Class we talk about email uh, application covering simple mail transfer protocol, IMAP, and POP3. And also we talked about the domain name systems. And today we will talk about peer-to-peer applications, right? So, so till now, the applications we have covered are basically based on client-server architectures. You talk about web, you talk about proxy server, you talk about email, or you talk about DNS, right? So these applications are client server based applications, right? So we know that there is another possibility, architecture possibility for application network applications, and this is peer-to-peer architecture, right? So in peer-to-peer architecture, there is no there is no such requirement that we have a server which is always on, right? And this means that arbitrary machines can directly communicate with each other. Peers now mean machines running the same piece of code can are providing services and utilizing services from each other, right? So now all these peers, all these peers are running the same piece of code, and now the clients or these peers can not only utilize services of the other peers provided by the others, but these clients are also providing the services, and this addresses a very important issue, scalability, and we say, and we'll also look at this in detail. This is self-scalable. This peer-to-peer architecture is self-scalable. Means if we add more number of peers, we do not, unlike client-server architecture, we do not need to have more servers. We do not need to add more servers into the network to provide uh, required delivery time and response time, right? So here adding more peers means that there are more peers participating in this file sharing or uh, any other sort of application process, right? So this is self-scalable. We'll see in a minute as well. But yes, peer-to-peer architecture, there are certain challenges, challenges in terms of trust, challenging in terms of management, right? Incentive to We need to provide incentive to the ordinary peers to be part of such a network, right? So there are many applications that are based on peer-to-peer. For example, BitTorrent, that we'll take example of in today's class. Streaming, we have ConCon and voice over IP. Skype, though it has been discontinued, but anyways, it's an example of peer-to-peer based architecture. Okay, so before we jump into any specific peer-to-peer application such as BitTorrent, let's have a quick comparison between the two, right? Client server and peer-to-peer based application. And for that, we need to let's have a look at the scenario. Okay, so first of all, uh, let me explain. Let us understand the scenario. So we have a server having a file of size f, right? So this is parameter, or this is parameter one, or the fact one that we need to know, right? And the server has a sending capacity us, right? Server can send data at the rate u sub s, and there are n number of clients. Client can download data at the rate of uh, d1, or you call it di, where I represents the number of the client. For example, one, two, three, four, right? N number of clients, right? So this is the download capacity of a peer or a machine or a client. And similarly, a peer has an upload capacity of u sub I. Okay, so we have file size. We have file size number one, which is f. Then we have the sending capacity of the server, upload capacity of the server, which is uh, u sub s, right? So upload capacity, server upload capacity, which is u sub s. Then we have peers download capacity, right? Which is d sub I, okay? And then peers upload capacity. Oops, excuse me. Then we have peers upload capacity, Okay, which is uh, u sub I. Okay, right now if we talk about the file distribution time in such an environment, given scenario using file server or client server application, So uh, we come across these transmission times. Number one, uh, this is the time. What is the time required to send one copy of the file? What is the time taken by the server to send one copy of the file? Obviously, this we can get by dividing the size of the file by server's upload rate or sending capacity. Right. So if I take the size of the file and divide it by the sending rate or the upload capacity of the server, I will get the time to send one copy of the file. But now imagine that there are n number of uh, machines. So what is the time required to send the n copy of the same file? That is n times uh, the time required to send copy of one copy of the file, which is nf divided by u sub s. Clear?
Yes, sir.
Okay. Then what is the time required to download one copy of the file, considering the client? Okay. So this is the size of the file divided by the um, di or the minimum download rate of the client. Okay. Right. Am I clear?
Yes, sir.
Okay. So we have three times: time to send one copy of the file, time to send n copies of the file, and time to download a copy of the file from the server by a client. Right. So what is the time to distribute n or copies of the file, or the file to n number of machines using client server approach? So this is always this the distribution time in client server is greater than equal to maximum of these two, right? Whatever is the maximum of these two will right. So the time required to distribute a file to n number of clients in client server environment is maximum of these two, right? uh, Either it is the time required to send n copies of the file, okay, or the time required to send or to time required to download a copy of the file. Okay, clear?
Okay, sir.
Right. So if I, you know, uh, so if you look at this distribution time, what if this n is increasing? What if this n is increasing? What will be the effect on this distribution time?
The time will take longer.
Your time will also increase. Okay, if the n number of if the n, which is representing the number of peers to whom we need to send the copy of the file, right? Okay, so if n is increasing, this will also increase the time required to distribute n copies of the file. Yes, no?
Yes, sir.
Yes. So if I want to keep the time same, right, so then what I need to do, right? So in order to make it scalable, right, so I need to add more servers, right? So if clients are increasing, right? Oops. If the clients are increasing, this requires that I need more servers into the network so that the distribution time remains the same. Okay, why? Because the U sub s is not increasing, right? Its U sub s is not increasing and n is increasing. Obviously, this will increase the file distribution time. Okay, so if n increases linearly, uh, so will be the case with the distribution time. We'll see in a graph uh, in a minute, right? But if I, taking the same scenario, talk about peer-to-peer file transfer, then again, we know this is the time required to send one copy of the file. Yes, no? That is, we divide the size of the file by the sending capacity of the server. Okay. This is the time required to download one copy of the file by a client. The size of the file divided by uh, the download rate of the client, or the minimum download rate. Okay, and now um, uh, this can be another time, and file distribution time uh, can be considered in this file distribution time, which is the maximum upload rate, where all the clients are sending or sharing or participating in this file sharing process, right? So this is an aggregate time, okay, which is now not only the server is sending, but also all the clients are also participating in this file sharing process. Okay, remember, in the previous case all we have only the server who was responsible for sharing the file, but now all the clients are also participating in this file sharing process, right? So now if I look at this file sharing, the distribution time in this peer-to-peer application or arrangement, it is greater than maximum of these three. What is this time? Time to send one copy of the file. What is this time?
Trying to download.
Download one copy of the file. What is this time?
To download n number of
Yes,
copies to
yeah,
send.
download or send n copies of the file. Okay, now if this n is increasing, right? If the number of nodes or clients are increasing, right? Okay, this remains the same. But what about this? What about this rate, right? Where u sub I is representing what? If you remember, u sub I is upload capacity of client, right? Okay. Now all the clients are also participating in this file sharing process, right? So if n is increasing, so is the upload capacity as well. Okay, so now if n increases linearly, so does the number of peers participating in this process. So try to have a look at this file sharing, or the distribution time in this file sharing, considering both peer-to-peer and client server applications. So this this graph, but this is a graph between file distribution time and number of files. Okay, so on x-axis we have number of files, on y-axis we have distribution time. Okay, so this represents what, right? So this graph represents what? Client server. If the number of files is increasing linearly, so is the case with the distribution time. Yes, no? We know, because now the formula, or the rate, or the file distribution time to send n copies of the file is n into f divided by u sub s. If n is increasing, right, so is the case with the file distribution time, right? So it also increases linearly. If we have more number of files to send, right? So obviously it will take more time. But look at this arrangement now. Now this graph represents what? This represents peer-to-peer file distribution time in peer-to-peer arrangement. Now if the number of peers are increasing, right, the file distribution time is not increasing linearly. Why? Because now the distribution time is equal to, or sending n number of uh, n copies of the file, is u sub s plus sum of the sending rate of all all the clients. Okay, so now if I have to, for example, uh, Send more number of files. Yes, n is increasing linearly, but so is the case with the upload capacity. Yes, no.
Yes.
Yes, right. So this is how, I mean, you can see that, it is self-scalable, right? Peer-to-peer is self-scalable. Why? Because we do not need to add more servers or resources in order to uh, maintain the file distribution time. But if I have to maintain the file distribution time, uh, in client server environment, I need to add more servers into this, right? So, in order to understand this, I would like you to solve to go through this example, right? For example, you have a file of uh, size f, uh, where its size is 15 GB. Okay, okay, and uh, the upload capacity of the server is 30 megabytes per second, right? And dmin, which is equal to say di, right, is equal to 2 megabytes per second. Okay, and ui is 300 kilobits per second, um, 700 kilobits per second, and 2 megabytes per second. Okay, and n is 50, 100, and 1000. Okay, so what I want you to do is, using these numbers, draw a similar graph, right, and um, present the file distribution time uh, required in client server and peer-to-peer applications. Okay, can you do that? Can you try? After the class, take this example, and I want you to solve it, right, and coming up with the same similar graph. Okay, so uh, you know what I need to solve, or to calculate the file distribution time, I need n, file size, server capacity, right, and I need what, u sub I. Okay, and in order to select the file distribution time, which is maximum of uh, three, from in the case of peer to peer, right, right. So you need also daemon as well. Okay, so you will calculate this time for file distribution and peer-to-peer arrangement file distribution time, and then this time, and then this time, whichever is the greater will be taken as um, uh, you know the file distribution time in peer-to-peer arrangement. Similarly, using those parameters, you will calculate the time to send n number of n copies of the file, and time to download one copy of the file, whichever is maximum will be taken as the file distribution time uh, in client server environment, and then you will draw this graph. Okay, yes, no,
So,
and I also want you to answer one more question, that after, when you will draw a graph, it will be something similar to this. Okay, and you can clearly see that the client server environment is not scalable. And if I ask you to also map this file distribution time of client server to this peer to peer, then you also need to come up with a formula to calculate how many how many servers are required how many servers are required for client server environment if we if we need if we need you know to have the same file distribution time, if we need to have the same or to have file uh, if we need to have file distribution time which is comparable to have file distribution time comparable to peer-to-peer. Okay, so what do you think, how many servers will be required so that the file distribution time is comparable to peer-to-peer, the file distribution time in peer-to-peer arrangement? Okay, and you need to come up with a general formula. Okay, uh, regardless of the scenario, whenever we have a file distribution uh, to calculate the file distribution time, and we want to uh, keep the file distribution time in client server environment comparable to the file distribution time in peer-to-peer. So how many servers are required? Okay, is this clear?
Yes, sir.
Okay, so now we can have a um uh, you know uh, we can go through BitTorrent as a sample application for this peer-to-peer file distribution. Right, torrents are very popular. Used to be right, very popular applications for file transfer. Okay, so now if we look at BitTorrent, so in BitTorrents we have we have a torrent. uh, Torrent represents the group of peers having chunks of a file. So, in BitTorrent, we divide a file in smaller chunks. We divide a file in chunk in 256 KB chunks, right? So, if a file is of one giga, gigabytes, right? So, we'll divide it in chunks of 256. Okay. So, torrent is when you go to server and you download a torrent for say Mad Men, for example. You want to watch movie Mad Men, right? You download a torrent. So this torrent actually contains what? Contains the list of the peers having chunks of Mad Men, right? So torrent means all the peers or the machines having chunks for the file that I'm looking for. Okay, and then we also need to have a server that keeps track of all the torrents, and we call such a server as we call it a tracker. So we have a tracker, which is a server which keeps the track of or record of peers participating in a torrent. Okay, and then we have a torrent. Torrent means a group of peers having chunks of a file, and a file is divided into, specifically talking about BitTorrent, a file is divided into chunks of 256 kilobits chunks. Okay, so now let's assume Alice arrives and Alice wants to uh, download a file. So first of all, Alice needs to search for the torrents on Tracker, because Tracker is the server keeping track of all the peers participating in a particular torrent. Okay, so Alice obtains the list of peers from the Tracker, means the torrent, and after getting the the list, Alice will make connection with those peers and will start exchanging chunks. Initially, Alice will won't be having any chunks, but over a period of time, Alice will obtain chunks as well, and will start participating in this file sharing process. Okay, so in the beginning, when Alice joins the torrent, she has no chunks to offer. Okay, but she will accumulate chunks over a period of time, right, from the other peers, and will also start participating in this file sharing process, and will get registered with the tracker, right? So now Alice is also participating. Alice has some chunks as registered in this torrent and is participating in this file sharing process. Right. So while Alice is downloading, she's also uploading chunks to other peers as well. Alice can come and go, right? So Alice, any peer can come and go, means peer can leave, right? We call it churn. Okay.
कीजिएगा.
Sorry. Right. So um, a peer can participate in this process selfishly or can leave altruistically, right? Can leave selfishly or can stay or altruistically stay in this torrent. I mean, can be part of this process, right? It's always healthy to be part of this process, right? So usually, while we are downloading some file from the BitTorrent, so we switch off the sending rate. We after downloading file, we just leave the torrent, right? So this is not healthy for this process, right? So it's always healthy to be part of, altruistically remain the part of the torrent rather than selfishly leaving it. Okay, so at at any given time, peers have different subset of file chunks because we have divided the file into chunks, right? So different peers have different chunks, right? So these different peers have different chunks of the file. Alice will request the rarest chunks first, right? The chunks which are rarest, uh, you know, uh, comparing the chunks available on the different, different peers, right? So this is important that every time we make a connection, right? In this case, Alice requests missing chunks from peers, rarest first. Okay. Okay. So after every 30 seconds, every peer optimistically unchoked another peer, hoping that the new peer will become one of its top four providers. Okay. And this goes on until we are done transferring uh, or getting all the chunks. Now, the quality of uh, you know this file distribution application depends on the selection of neighbors. Okay, how well or how quickly I'll be able to download um, chunks. It depends on how I am selecting my neighbors. For example, if I have say 10 chunks of a file and I select a peer who also has the same 10 chunks, will there be any advantage of having this peering relation or this new neighbor? Question. Right? So what I'm saying is, if the neighbors have same chunks, right? Is there any advantage?
No, sir.
No, it's not. I have 10 chunks. Lukman also has say 10 chunks and the same 10 chunks. What's the advantage of making Lukman my neighbor? Right? There's no advantage. Right? So the quality of BitTorrent application depends on the selection of Guriye,
Selection of the neighbor.
neighbors, and the neighbors are selected based on probability. Right? So आपको मेरी वन नोट्स की नजर आ रही है?
Yes, sir.
Yes. So uh, BitTorrent, or for example, any other torrent application, BitTorrent quality depends on selection of neighbors. Okay, and neighbors are selected based on probability. Okay, so we need to calculate probabilities to see. Okay, if I'm making Lukman my neighbor, what is the probability that Lukman has chunks uh, that are of interest to me? Okay, right? For example, for example, what is the probability that Bob has same chunks as Alice has? Okay, what is the probability that Bob has same chunks as Alice, right? Has has given um, given that the number of chunks Bob has are greater than the number of chunks Alice has. Okay, given NB n sub b here represents the number of chunks Bob has are greater than equal to the number of chunks Alice has, right? So I want to make Bob wants to make Alice a new neighbor, right? So Bob will calculate, okay, what is the probability that I have the same chunk as Alice has, given that my chunks are greater than equal to my number of chunks are greater than equal to the number of chunks Alice has, and this can be calculated. Um, you know, means this probability that Bob has all the chunks that Alice has can be calculated can be calculated using uh, combination notation, right? Is equal to, okay, there's no.
Yes.
This is known as परेशान नहीं हूँ मैं आपको explain करता हूँ. This is known as combination notation, right? Okay, this form Cn of n, right? This form is known as, बोलिए, combination notation. This is about uh, selecting n sample out of total sample space, selecting n out of n, right? And is known as combination notation. There are different ways in which we can solve a combination notation, right? Um, in fact, there are three three different ways we can be used to solve combination notation. Okay, so number one is binomial theorem or coefficient. right? Which is this NCR, or using NCR function where uh, n selects R, okay, or using uh, factorial, okay, which is equal to n factorial divided by R factorial into n minus R factorial. Okay, यस नो. सो थोड़ी देर के लिए मैंने इसको यहाँ पे रोक दिया है, अभी मैं आता हूँ वापस इसकी, राइट. आई कम बैक टू दिस, आई लीव इट विद द क्वेश्चन मार्क. ओके. So just want to explain that this probability is based on combination notation, right? Selecting n number of chunks out of total n chunks, right? And the combination notation can be solved using binomial theorem or NCR function or factorial, right? Where n factorial divided by r factorial into n minus r factorial. Okay, just no. For example, for example, if I say if I toss a coin 5 times, what is the probability of uh, having a head 3 times using this combination notation, right? So I can solve it using the formula, the factorial, this formula that we uh, for the factorial here, okay? And okay, so n is 5, 5 factorial divided by 3 factorial, yes, no, into 2 factorial, yes, no. बोलिए शाबाश, है ना. If I, you know, if I just put these value in this formula, right? So this is how it looks like. Yes, no,
Yes, sir.
yes. अगर आपको समझ नहीं आया आपने मुझे बताना है, right? So मैंने वहाँ रोक दिया उस पर थोड़ी देर के लिए. Just I'm trying to explain कि यहाँ पे हमारे पास combination notation से क्या. I'll give you another example before I go back to the probability that we were discussing earlier. Okay. So this is equal to 5 into 4 into 3. Yes, no. Okay. Into 2's factorial, and this is 3 factorial, 2 factorial, right? Yes, no. So this 2's factorial will be cancel out, and this 3's factorial is 3 into 2 into 1, right? Yes, no. ये समझ आ गया आपको? जी.
Yes,
Right, so I'm writing 5's factorial is 5 into 4 into 3 into 2's factorial, right? No. Yes, no, right? 3's factorial is 3 into 2 into 1, and into 2's factorial. So 2's factorial will be cancelled out, right? So this is what 5 into 4 into 3, okay, divided by 3 into 2 into 1. This is बोलिए क्या है 60 divided by 6, right? 10. And now if our coin is tossed um, 5 times, so this means 5, sorry, 5 3 divided by 2 raised to power 5. So 5 3 is 10 divided by 32. So I will get the probability. Okay. Yes, no.
Yes.
right? कोई confusion है तो आप पूछिए शाबाश नहीं है तो I'll move on. Let me give you another example. What is the probability, for example? Um, let's assume that I have a set of alphabets, five alphabets, right? N is A, B, C, D, E. Okay. And if I ask you, uh, what is the uh, possibility of having three alphabets, uh, arrange three alphabets in order, right? And what is the possibility to have such total combinations? So I can again calculate that three alphabets, right? So again, the problem is something similar to this. So the number of ways I can arrange three alphabets is equal to arrange three alphabets is equal to um, 5 into 3 into 4 into 3, okay, which is equal to 60, right? So there are 60 possible ways in which I can arrange three alphabets, okay. And what is the possibility that three alphabets can be in order, right? So for that I have 3, 2, 1, which is equal to 6, and the total combinations would be 60 divided by 6, right? So what I want to say is that these probabilities can be calculated with combination notation, right? And the combination notation uh, can be solved using either binomial theorem or NCR function, or most importantly that we are familiar with and you're familiar with is uh, factorial. Now coming back to this probability, what um, what this represents, this value, n here represents the total number of combinations or chunks of the file, minus na are the subset of the chunks with Alice. So what is this n minus na representing? The chunks that Alice does not have. Okay, this represents what? Chunks that Alice does not have. Yes, no? And this is what NV are the chunks, subset of the chunks with Bob, minus the subset of the chunks that Alice has. This is what the difference between the Alice and Bob's chunks. The chunks after having a difference uh, between the Alice and Bob's chunks, right? So this is the difference between um, Alice and Bob's chunks. Yes, no? मैं आपको एग्जाम्पल से भी समझाता हूं, पहले ये समझ लें. And what is this? Bob's chunks, right? Total auto total chunks. Okay. So let me give you an example for this probability. So the so so let's assume, um, but the very important thing you need to understand here is that this probability, um, or this formula provides the probability that Bob has all the chunks Alice has provided Bob has some fixed chunks. Okay, when both are selecting chunks separately and independently. This is very, very important. And let me write this formula here again so that we can refer to this. This is equal to, okay, right? So what this probability represents, this formula, this provides the probability that Bob has all the chunks, Alice has, provided, this is very important to note, provided Bob has some fixed, n sub b, right, chunks, um, when both when both are selecting chunks separately and independently, right? Independently, okay? Separately and independently. This is very important, and let me read it again. So this provides the probability that Bob has all the chunks Alice has, provided Bob has some fixed NB, some fixed chunks, when both Alice and Bob are selecting chunks separately and independently. And let me, give you an example now. So let's assume n is equal to 10, okay? And the number of chunks out of these total chunks, Alice has three chunks, and Bob has some fixed chunks. Say, fixed chunks are, let's say, five. This number is fixed, okay? Now, um, how can I calculate this? Again, I will put these values into this formula. The probability that Bob has all the chunks that Alice has is equal to this formula, and let me put this value minus 3, right? So now, this means what? This means now I have these values 7, 2, and 10, 5. Any confusion up till now? The important thing here is the number of chunks Bob has are fixed, right? Yes, no. Okay, and now we can calculate these. I can calculate the value of this combination notation. I can calculate the value of this combination notation. Yes, no. Can I calculate the value of this
Yes,
combination
sir.
notation? Answer is yes. How? Remember this formula? Yes, no. How to solve a combination notation using a factorial? So I will just put the values here, right? So this is what 7 factorial divided by 2's factorial into बोले क्या होगा 5 factorial. Yes, no.
Yes, sir.
Yes. Similarly, I can solve this as well. बताएंगे क्या? 10 factorial,
10 factorial in numerator divided by 5 factorial multiplied by 5.
5 factorial. Okay, can you solve this? Let me do it here. So this is like 7 into 6 into 5 factorial. Yes, no? This is 2 into 1 into 5 factorial, right? So we'll cancel out this 5 factorial, right? And we'll have 42 divided by 2. And this will come out to be 21. Yes, no?
Yes, sir.
Yes. And if I similarly try to solve this, so this is 10 into 9 into 8 into 6 into 5 factorial. Okay. And then we have what? Uh, 5 into 4 into 3 into 2 into 1 into 5 factorial. Okay. And if you try to solve this comes out, I think, please verify करने 30,240 divided by 5 into 4 into 3 into 2 is 120, right? And this comes out to be 254 or 252, sorry. Okay. And now let me put these values here. Okay. So 21 divided by 252, okay, or 1 divided by 12, okay. And if I solve it, I have this 0.833, 0.0833, or 8.33%. Okay. So I will select the neighbor having the low probability of having the same chance, right? So you have to select. So important thing is select neighbors that have low probability. Okay, low probability of having the same chance as yours. Okay, so I will, when I am making a neighbor, and what is the assumption I am making here? That Bob has what? Burishabash.
Fixed
Bob,
number of
yeah, fixed. This is very, very important, right? Because if it is not fixed, we'll have to calculate the probability in a different way, right? So let's say यहाँ था कोई confusion है तो बताइए.
no, sir.
बाकी लोग अगर कुछ कहना चाहते हैं. Let's say NB is not fixed. NB is a range. Okay. So let me modify this now. Um, Now we want to calculate probability where NB is not fixed and NB is in a range. Let's say NB is not fixed, right? NB is 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 in a range. Okay. So now for the different values of NB, what is the overall probability, right? So now, look, we calculated the probability in the previous example for one value of the NB. NB was what? 5, right? But if NB is not fixed, then we have to calculate the overall probability, right? That Bob has all the chunks that Alice has, right? For this means for different values, this means for different values of NB, what is the overall what is the overall probability uh, that Bob has oh, that Bob has uh, okay. And the important thing is that occurrence of each of the value of NB is equally likely, right? This is very, very important, right? Occurrence of occurrence of each value of NB is equally likely. Okay. Okay. So now we will need to calculate the overall probability, right? And we can calculate this by putting values in this formula. So probability for NA is 2, right? Is equal to 1 by N is 5, okay, right? Into what? Into, now we have to calculate the probability for each of the possible value of NB, right? So, for example, first we'll have N is 5, 5 minus 2, and then for the first value of NB, which is 2, 2 minus 2, right? What will be, yeah, NB is 2. And here I'm using this formula. Right? Let me write it over here for your ready reference. The same formula that we used in the first example to calculate the probability of one value of NB. N minus NA, NB minus NA, right? So I'm using this formula, okay? Yes, no? Plus the probability for the next value, okay? Then it will be what? I'm just putting the values straight away. I'm not, minus up करके यही value आएगी, okay? चेक कर लीजिएगा यही values आती हैं कि हाँ. Yes, no? जी. Yes, no. Okay. And if you solve it and multiply, you solve this by taking using factorials formula that we have just discussed to solve binomial theorem, and you multiply it with 1 by 5, and you do the same for the rest of the uh, probabilities. So we'll get this value 0.02 plus 0.06 plus 0.12, right? So which comes out to be zero point 0.2, I mean 20%. Okay. So 20% is the overall probability that Bob will have all the chunks that Alice has. So now 20% is the overall probability um, that Bob will have all chunks that Alice has. Okay. So how I'm getting this value, I leave it to you. I, I think you can calculate it now. So I will solve it, right? And I will multiply this with 1 by 5, and similarly I can get the rest of the values. Okay. ये आप सॉल्व कर सकते हैं, हम करके हैं ऊपर दो एक एग्जांपल्स में.
Yes, sir.
Yes, you can do it, right? It's easy, not difficult, right? So again, now we can calculate the probability considering that the number of chunks that Bob has is are not fixed but in a range, right? So similarly, I can also calculate the probability that I have a chunk that any of my neighbor is interested in, right? Any one neighbor is interested in. Similarly, I can calculate probability that uh, I have chunks that any one neighbor is interested in. Okay, so this can be calculated using this formula. You can calculate this probability, which is a this is known as failure probability. Okay, so this says okay, I have at least one chunk which is uh, uh, right of interest to any one of my five neighbors. Okay, so this is the failure probability. The success probability can be calculated if I subtract this from the total probability, right? So this is n a is equal to 0 to 1. Okay, so this is success probability. Okay, right? So, so again, if I can you calculate this? Yes, we just did. Okay, You will multiply it with 1 by n,
Yes.
right? And then you will take it raised to power the number of neighbors, okay? And you will subtract this from the total probability one, and you will get the success probability that we have at least we have some chance that at least one of our neighbor is interested in, right? So the purpose to present all these probability to you is uh, to emphasize the fact that the BitTorrent's efficiency depends upon the selection of the neighbors done by calculating probabilities, right? So let me write it here. So BitTorrent, BitTorrent's efficiency depends upon selection of neighbors done by calculating different probabilities. Okay, probabilities, right? Any question? Get back to me in the next class, okay? And as far as this example is concerned related to the distribution time of peer-to-peer and file sharing, I mean peer-to-peer and client server applications, you have to solve this uh, by making a table, and then using that table for client server and table for peer-to-peer, and then you need to generate a graph using that table, right? Okay. And then also you need to come up with a generic formula that will tell me that how many number of servers are required if if I want to match the distribution timer in that of peer-to-peer applications. Okay, right. So uh, now we'll move to the next topic of discussion, which is video streaming, and here I will talk about content distribution networks as well. Okay. So, if we talk about different video streaming applications such as Netflix, YouTube, Amazon Prime, and others, for example, it is reported that at least 80% of the residential traffic is based on consumer internet bandwidth is based on um, uh, these streaming videos, right? This is a major consumer, of the internet bandwidth. Okay, this video and we have not mentioned here from the TikTok and the others, right? So the streaming video traffic is the major consumer of internet, is about 80% of the residential traffic is okay, streaming video traffic, right? And this becomes challenging. Why? Because there are about 1 billion users, right? And then we have to scale it up. For example, how to reach 1 billion users, and this becomes more interesting. This is more challenging, depending upon the heterogeneity of the users. I mean, different users have different capabilities. Some users have wired connections, some users are using mobile phones, or they have mobile connections, for example maybe 4G, 5G, or maybe Wi-Fi, right? Some users have a rich bandwidth, then maybe the other users have poor bandwidth, right? So this becomes again challenging, how to provide these video streaming services, which makes up of 80% of um, uh, the residential ISP traffic, right? And considering especially that different users have different capability in terms of the type of network, uh, in terms of the bandwidth availability. Okay, and the solution to this is um, to come up with file distribution or video streaming application, which is distributed in nature, right? And this distribution in nature is in fact uh, the application specific infrastructure is distributed in nature, right? So we'll see in a minute, and this will achieve using content distribution or delivery networks. Okay, but look, before we really jump into video streaming, first of all, we need to understand that the basic of any a video is. I mean, a video is a sequence of frames, right, which are displayed at a constant rate. For example, if I n number of frames and if I display like 40 frames per second or 28 frames per second or 20 frames or images per second, it will create a video. Yes, no? Yes. So a video is essentially a sequence of images displayed at a constant rate. Okay. For example, 24 images per second. Right. Okay. Um, so whereas a frame, um, a digital frame or an image in this case can be understood as an array of pixels. Each pixels each pixel is represented by bits, maybe some by using some fixed bits in a constant bit rate, or maybe using a variable bit rate in VBR. Okay, so now what I want to say is that this you know this image is represented as an array of pixels. So these are the different pixels, right? And each pixel is encoded using or is being represented by some fixed bits or maybe by variable bits depending upon the encoding scheme, right? But before we really uh, look at the variable bit rate or fixed bit rate, we can we can improve this digital image encoding in terms of spatial encoding or temporal encoding. Now the spatial encoding is, so look, if I have to represent all these pixels with some uh, n number of bits, right? So in this case, I will represent, you know, uh, n number of pixels with n number of bits, whereas all these pixels have the same value. They have the purple color, right? Simple, right? So in spatial encoding means what? This means that instead of sending or representing n values of the same color, right? So in all these pixels, right, I have the same values, the same color, right? So I do not need to represent each of the pixel value with n number of bits, right? So instead of sending n values of the same color, means all purple, I will only send two values. One is the color value, which is purple, and the number of repeated values. So one value representing this color, and the next value represents what? N number of repeating values, right? This is known as spatial encoding. Encoding in terms of space, in space, means encoding within an image, right? Spatial encoding is what? Is an encoding that we do or implement within an image. Okay. There is another sort of encoding. So we'll save a lot of while we're encoding an image, and or we are encoding a video. We'll save a lot of or we can represent an image or a video with less number of bits if I make use of what? Spatial encoding. Yes, no. And we can also use temporal uh, encoding in terms of time. In in time I mean, in terms of time means what? That we will only send the difference between the, so this is frame number I, and this is frame next frame, which is I plus 1. Instead of encoding the whole frame, I will only encode the difference between the two frames. I will send the difference between the two frames, right? So temporal encoding is from one image to the next. I will only send the difference between I and I plus 1, the next image, right? So temporal encoding is what? Instead of sending the complete frame at I plus 1, right, we will only send what? The differences from the previous frame I. Again, saving a lot of uh, a lot of bits to represent images or a video, right? So it's very popular that we do the both, right? Temporal and spatial encoding. And then I can encode, after doing the spatial and temporal encoding, I can do encoding at a constant bitrate, means regardless of the details of a pixel, right? I use same number of bits to represent that pixel, right? This is known as constant bitrate. Or I can do variable bitrate. I mean, depending upon the details and, um, details uh, in uh, a pixel, right? I will use variable number of bits. अच्छा ये दोनों बातें सही हैं, यहाँ पे भी मैंने कुछ और बात की है, यहाँ पे कुछ और लिखा हुआ, right? So variable bitrate में क्या कह रहा है? Video encoding rate changes as the amount of spatial temporal coding change. This is also true. This is also true that if we have, if a pixel is representing more detail, I mean, I want to represent it in, greater at a greater, rate, or providing more quality, I'll use more number of bits to represent that pixel. Okay, आपकी बात समझ रहे हैं? Right, so I can encode a video using constant bitrate and variable bitrate after doing spatial encoding and temporal encoding, and that's why we have different encoding standards. Right, we have MPEG 1 that we use for CD-ROMs, MPEG 2 for DVDs, and yes, we are interested more with MPEG 4 that we use in internet nowadays. Right, that can give us, data rate of, can be encoded at 12 megabytes per second. Right? Okay. Now, so what are the main challenges? Right. So let's assume that this is a video streaming server, a video that is stored on the server, right? And here is a client who wants to access the video, right? There are a lot of challenges involved while accessing a video, right? Number one is that this bandwidth between the client and the server vary over time. It's not same as all. It's not same always, right? With the changing network conditions such as congestion levels, right? This bandwidth varies. Yes, no.
Yes.
Yes, because of the access network, because of the core network, because of the load on the video server, etc., etc. This changes. This is challenge number one. The challenge number one, and the challenge number two is, what about the losses? For example, so this is challenge number one, right? But this bandwidth changes between client and server. And the other challenge is, what about the packet losses? What about the delay due to congestion that will affect the playout time? I will talk about this playout time in a minute, right? This can result into poor video quality. Okay, so we want to, regardless of the available bandwidth, regardless of the network changing network conditions because of congestion levels, or because of the variation in access networks or code network, right, or the load on the video server, we want to provide reasonable quality video to the client. Okay, this is the challenge of streaming stored video. Okay, um, for example, uh, this is the rate at which we recorded the video, right? This is a graph between the cumulative data and the time, right? So we recorded the video at 30 frames per second. Okay, so we recorded 30 frames per second, and we wait, and then we again record 30 frames per second, and then so on and so forth. Okay, this is our recording rate, and this is how we stored the video on the server. Okay, and the server will send the video at the same rate, having this identical, cumulative data representation. Yes, no? Is there any difference between the two? बोलिए. Is there any difference between the two? हम्म. आप हैं. जब मैं आपसे सवाल पूछूं तो फिर जवाब दिया करें उसका.
Can you repeat?
Yeah. Is there any difference between the two? The rate at which the video was stored on the server at the rate, and the rate at which the server is sending the video? No. Okay. is the same. Server is also sending 30 frames per second, right? That's why we call it streaming stored video, right? Now server is sending this video to a client, and obviously this involves certain network delays. Yes, no? Yes. Okay. After this much time, the client will start receiving the video. Okay, so after this time, the client will start receiving the video, and ideally, after this time, right? And ideally, client will play the video at 30 frames per second.
Difference.
Yeah, an ideal scenario, right? So the video is stored on the server, and the server at 30 frames per second, and server is also sending video at the same rate, streaming the video at the same rate. And now, after some time, obviously there are network delays involved. It will take some time to reach from server to the client, and now the uh, client module, part of the application has started playing the video 30 frames. So this is a very, ideal scenario, right? But there is an important thing to note here. While the client is playing, this part of the video, right? Server is done transmitting some, later part of the video, right? That's why we call it streaming. Streaming is what? At this time, client is playing, at this time, this very time, client is playing out some early part of the video while server is still sending, right? Later part of the video. And we call it what? Streaming. Okay. But nonetheless, this looks a ideal scenario. But what about the continuous playout constraints? I mean, the playout time, the time at which you are playing out must match the time of the server. I mean, the original timing. But if there is a mismatch, right? If there are variable network delays, I mean, there is jitter, variation delays known as jitter, right? Client needs to do what? You must have seen this
Would have to
screen
wait.
a lot. Yeah, client side needs to buffer to match what? To match the continuous playout constraint. What is continuous playout constraint? That the playout timing must match the this must match the original timing. Okay, and if there is a mismatch because of the delay, we we may see a screen something similar to this, where the client needs to buffer so that client can fulfill this constraint, which is continuous playout constraint. Okay, okay, but there are other challenges as well. For example, what about client interactivity? We pause, we do fast forward, we do rewind, we jump in between the scenes throughout the video. Yes, no?
Yes, sir.
Yes, these are other challenges, right? And yes, video packets can also get lost, then needs to be retransmitted, right? So this is not straightforward, right? So there are many challenges that we have to take care of while implementing streaming stored video. Okay, so for example, let's talk about this playout buffering. So this is the the rate at which the server is transmitting, which is exactly the rate at which the video was stored at the server. Yes, no? Yes,
Yes,
right?
sir.
But look at the rate at which the client is receiving. Is it the same? Is it the same perfect
No, sir.
staircase? So I mean, how do we really implement how regardless of your compromised internet connection, still you are able to have watch, for example, Netflix video, right, with a reasonable quality, right? This is because the streaming multimedia application implement a protocol known as Dash. There are other details as well, but the fundamental, uh, protocol is known as dash. Dash is dynamic adaptive streaming over HTTP. Okay, so what we do in this dash is that the server divides the file into multiple chunks. Okay, so if I have a video file, the video file will be divided into multiple chunks, right? Uh, for example, if I take example of Netflix, so we have this chunk of 4 to 6 seconds. Okay, so this is point number one, right? That the file is divided into multiple chunks. An example uh, can be taken of Netflix, where the file is divided into 4 to 6 seconds chunks. Number one. Number two, each chunk is encoded at a different rate. So this is number one. Number two is each chunk is encoded at different rate. So uh, आपने अक्सर ही एक्सपीरियंस किया होगा while you're watching YouTube video, right? So the quality of YouTube video is automatically adjusted based on the quality of your internet connection. You can play it at 450p or 720p or 104p, depending on 4K, for example, which is H.265, depending upon what? Depending upon your network connection. Okay. So number one is to divide the file, say the video file into n number of chunks, and Netflix 4 to 6 second chunks, and then you need to encode the chunks at different rates. Okay, different different rate encoding stored in different files, and these are stored separately. And these files are replicated on different content delivery or distribution network nodes. So number one is to divide the file into different multiple chunks. For example, in Netflix, 4 to 6 second chunks, and then to encode different chunks at different rates, and then store different chunks at in different files and at different places, right? And then we create a manifest file, right? A file which provides the URLs of all the different chunks of all the files uh, encoded at different rates, stored at different places for a particular video. I repeat. Okay. So the manifest file, what it does is it contains the URLs for the different chunks. Obviously, different chunks are of different quality. Okay, means are encoded at different rates and are stored at different places. Okay, and in fact are also replicated in various content distribution network nodes. Right, and the role of the client is very, very important in this case, right? So the client needs to be intelligent, right? The client part of the application, in the case of Netflix or in the case of any streaming video application, needs to be intelligent. Client needs to periodically estimate client to server bandwidth by using weight determination algorithms, right? So client monitors, for example, in Netflix, client monitors this client server uh, bandwidth file. It requests one chunk at a time, right? And if your connection quality is good, we'll go with the maximum encoding rate that can sustain given the current bandwidth requirement, okay, or available bandwidth, okay. So if my bandwidth is doing pretty well, for example, I'll go with 1040p. Okay. If my bandwidth is compromised, I can degrade it to um, a rate to a lower rate. Okay. For example, 480p, because a copy of the chunk is encoded using 104p, and the same copy is also encoded using 108p or 72p. Okay, right? So the client uh, part of the application will choose the maximum encoding rate, for example, 1040p or 4K, for example, which is can be sustained based on the current bandwidth, and it can use the different encoding rate at different points in time, depending upon the available bandwidth at that time, and maybe from a different server as well. Okay. Yes, no. Okay.
Yes,
So
sir.
okay. So client is intelligent because it determines what, when to request a chunk, right? So that buffer starvation or buffer overflow does not occur. Okay. So we don't want, you know, to have a scenario where we have, okay, this is the original transmission and this is what we are receiving, right? So we want the um, chunk request to ensure that we do not have buffer overflow or buffer starvation. So this is my, layout buffer to play this ideal, you know uh, play out matching the original one, right? So I need to ensure that there is no buffer starvation or buffer overflow. Okay, number one. Number two, what encoding rate to select? I will select the higher quality if I have higher, sufficient bandwidth available that can sustain that quality, or if I have a problem with the internet connection, I will downgrade the quality of the chunk. Where to request the chunk from, right? The client can request URLs, URL server that is closer to the client or has the highest available bandwidth. Okay, based on the proximity or the availability of content that I'll talk about in a minute. Okay, so client, the role of client is very important. So if I, some of the streaming video is what is a combination of encoding, how the images or the video is encoded, and most importantly, this dash protocol, right? In which we divide the video into different chunks. Different chunks are, different chunks are encoded at different rates and are placed at different places and are replicated in CDN. And then, most importantly, the client part of the application, where the client needs to uh, maintain a play up buffer, and it also needs to select the right encoding rate and from the right server. Okay, right. So now, if we talk about the streaming video, in streaming video, we just talked about that. What we do is that we replicate the files into various CDN nodes, right? So CDNs CDN is known as content distribution network or delivery network, we get, right? So the challenge is how to stream the content, selected from millions of the video to the hundred and billions of users simultaneously, hundreds of thousands of users simultaneously, right? This is a challenge. So one option is that we have may maintain one large mega data center. We know this. We know the problem with centralized approach. This can result into single point of failure. Maybe uh, uh, we end up having a lot of traffic, network traffic, result into network congestion. It may result in long path for distant clients. Right. If we have one data center, we also covered this in our discussion on DNS. Okay. So, and it will not scale up, right? So the right approach is to go for CDNs, right? Distribution networks. So the option two is to go with this CDN where we have two approaches, okay? And these approaches are known as server placement policies or strategies, right? These are CDN server placement strategies or philosophies, okay? So we can, there are two options. We can enter deep, okay, can push the CDN server deep into access networks, in access ISPs, closer to the user, okay. Right. For example, Akamai is a popular CDN provider, okay, and ये थोड़ा ओल्ड स्टैट अभी मैं रिसेंटली आपसे शेयर करूंगा. In 2015, uh, Akamai has one. Akamai has more than 240,000 servers in more than 120 countries. So we are placing server closer to the user in access ISPs. Okay, we know the access ISPs and access networks, right? Or the other approach is, or the CDN server placement strategy is to bring home, right? So we have smaller tens of large clusters in point of presence near the access network, and this is approach by used by Limelight. Limelight is another you know uh, famous CDN providers. Okay, and we can use the both as well, right? For example, यहाँ तक आपको बात समझ आ रही है? Because we have to replicate the files on CDN servers, right? So the CDN in content distribution network, CDN server placement strategies can be either enter deep or bring home. Enter deep means we are placing the server closer to the user in access networks, in access ISPs, right? For example, आपको recent stat भी हम देखते हैं. For example, Akamai in till 2015 has more than 240,000 servers in more than 120 countries. And in Bring Home, this is another approach where you can have larger you know data centers or clusters near the point of presence of the application provider. Okay, this is the approach used by Limelight, and we can have a mixture of these two as well. Misal ke taur pe, for example, if I talk about Google, Google has three tier. Google has three-tier um, architecture, right? Tier one is having 8 mega data centers. Okay, each having servers in the order of hundreds uh, of thousands, right? Each having servers in the order of hundreds of thousands, right? And tier one is used by Google for dynamic, uh, used for dynamic content. Using this, Google generates or provides us all the dynamic content. Or, for example, email, Gmail, right? Or search, right? So tier one having 8 mega data centers across the globe, right? It has huge server farms, right? And tier one is used to serve dynamic content, to maintain emails, and to uh, provide search results. Okay. Then we have tier two. Tier two has 30 bring home, right? So again, we'll see that Google follows a mixture of these two CDN placement strategies: enter deep and bring home, right? Tier two has 30 bring home CDNs. Okay, right? CDN clusters. Okay, each having a size of hundreds of, each holding hundreds of servers. Okay, and tier 2 is used for static results, and also YouTube videos are also used for or generated or placed at this tier 2, right? Used for static content of our websites, and YouTube videos. Okay, and uh, in tier three, Google has used this approach enter deep, where Google has hundreds of servers placed in different access ISPs. Right, this is enter deep. Hundreds of CDN, CDN, CDN servers, right? Using enter deep, right? Are placed in access ISPs. We use this for or to cache popular content. Okay, to cache popular contents. Okay, so again, if I look at if I look at Google, so Google uses a mixture of these two approaches, which is enter deep and bring home. Okay, so but these are known as uh, content distribution, server placement strategies. Okay, yes, no. Netflix also uses mixture of these
Yes.
two. Oops. Netflix, come on. So Netflix uses both, right? Okay, we'll see in a minute. So if we look at Akamai today, there are more than 360,000 servers, right? In more than 4,200 locations, right? In more than 840 cities and in more than 135 countries. And these Akamai Edge means uh, entity based approach are having 100 plus million hits per second, and they provide us 7 plus trillion 7 plus trillion deliveries per day and 175 terabits per second. Okay, so imagine the scale of the data transfer, the services, right? So how does Netflix work? If we take this example, so अभी आपकी क्लास है 1:30 और अगली दफ़ा फिनिश कर लेंगे, अभी 5 एक मिनट लगेंगे हमें, बताइए. How does Netflix work? Just to put everything in perspective. So a Netflix have this open connect CDN nodes, right? So what Netflix does is it stores the copy of the content. For example, I want to access Mad Men, right? So I want to, you know, I want to watch this movie Mad Men, and what Netflix has done is that it has stored the copies of the Mad Men, the chunks of the Mad Men encoded at different rates, placed at different CDN servers worldwide. Okay, so here are different locations. Remember this diagram, you should, right? Uh, this represents our right. So yeah, so there's a lag here. So remember this diagram. This represents what? This represents the access ISPs and regional ISPs and internet exchange points and tier one ISPs. If you remember this diagram, okay. So what we have done is the Netflix has stored the different chunks at different servers, following the approaches, both the approaches, enter deep and bring home. Right? Most importantly, CDN has placed their servers near or in the access ISP near the access network, and these servers are uh, these servers are known as specialized edge cache servers, right? And we call it OCAs. We call these servers what? Open Connect appliances, right? OCAs, okay, right? And these OCAs are specialized edge cache servers, okay? And based on this Open Connect CDN, right? So okay, now, for example, I want to watch Mad Men, right? So first of all, the subscriber will request the content from the service provider, and the service provider will, in return, will share a manifest file. What a manifest file includes, कौन बताएगा? So in this request, I'm saying
So the
okay,
manifest file includes the updated URLs basically
URLs,
for the upcoming
URLs, right? And
games.
URLs having what? URLs having the chunks encoded at different rates, placed at different CDN servers. Yes, no, yes. Okay. In addition to this, let me add one more point. Uh, in addition to OCAs, Open Connect appliances, uh, Netflix also has this settlement-free interconnection agreement with different peers. SFI, right? Settlement-free interconnection, right? SFI. This is a peering agreement with the other peers that we will not charge each other, right? So we will send. So this is a peer agreement between networks where no money is exchanged, and the data of each other is sent. Okay, right. So after receiving the manifest file, the client will start, depending upon the client node has to be, or the part of the application has to be intelligent, right? So based on the uh, you know weight determination, um, uh, uh, you know, uh, weight determination algorithm, it should be rate determination, right? It's not rate, it's rate determination. Please make this correction. Rate determination, okay? After, based on this rate determination algorithm, the client will, uh, you know, request a chunk from an appropriate server, okay? Now I will start receiving what uh, the chunks of the video madman. But if there is a change in the network delay, if there is some congestion, there is a load on the server, I will change this server with another server, right? So previously the client was receiving data from this server, and now I've changed the server because of the delay, or maybe the load on the server, right? So you can think of CDN as over the top overlay network, OTT, right? So in our network of this access ISPs, regional ISPs, internet exchange points, tier one ISPs, and on top of it, this is a layer overlay network where we have placed, CDN nodes at near to the user in closer proximity, so that user can, uh, access data, can select an appropriate node based on the different, uh, based on the quality. Okay, right? So this also leads us to another discussion, which is CDN selection strategy, right? So CDN placement strategy क्या थी बोला? Enter deep and bring home. Okay. So similarly, we have how this client will select a server, either this server or this server. Okay. Let me, yeah, right. Let me go back to this diagram. How we will select, why we will select this server or this server, or for that matter, any other server, right? It depends on our CDN server selection strategy. CDN server selection strategy. There are two approaches that we follow, right? One is DNS based, and the other is uh, application based. I will select this client will request a server either based on DNS or based on uh, the application. Okay. Okay. When I say it's DNS based, this means what? A server will be selected based on a geographical proximity. Okay. I mean, this I will select a server which is closer to my location in my access ISP, for example, or in an internet exchange point near to my access ISP. Okay, so DNS based means it is based on geo. It is based on geographical proximity. Okay, closeness. Okay, the server which is closer to me will be selected. Okay, I will only select the other server if I am experiencing a problem with the server. Maybe the server has a lot of load, maybe the network is congested at the moment, and I can switch to any other server. Okay, but the choice is based on what? Geographical proximity. Maximum, I mean, if I have an IP address, I can always get the location of uh, that IP address. Okay, so if I have IP addresses, I can get the location and I can connect to the location which is closer to me. Number two is network connection. Network uh, connection conditions. Network, I can call it network condition. So I will select a server based on geographical proximity and network condition in DNS based. And also the third important factor will be load, right? If I talk about the first approach in selecting a DNS server, it depends on either the geographical proximity, closeness of